Hey everyone, and welcome back to another video. In this one, we are going to talk about AVL trees, which are binary search trees which are able to balance or rebalance themselves. Now, data structures and algorithms are an integral part of software development, but it might be the case that you can develop web applications or anything without having knowledge of data structures or reading through them for years. It's quite possible. But if you learn these are going to help you out at some point in your career. So before we start the video, I would highly suggest that you subscribe to the channel. That really helps the channel grow. It's free of cost and it helps the content push out to all those developers. Now let's get started. So before we jump into AVL trees, let's understand binary size trees. And if you have not watched my video on binary size tree with JavaScript, go check it out. You're gonna understand a lot better than that. But here I'm going to give you a really quick overview of binary size trees. So what are binary size trees? A binary size tree is a tree which has nodes having two children at most, and both of the child have some special situation. Here you can see that each child has, or each node has, a left child which has a lesser value than the node itself. For example, we can take a look at this node 2. So here you check the node 2 and the left child of this node 2 has a lesser value than the node itself. So let's say the node is n and it is 2. The left child here is less than n, which means that 1 is less than 2. And the right child, let's call this r, the right child is always greater than n, or the node itself. And this is true for the entire tree. The entire tree, every node, this case would be following. For example, if we have a look at 5, if 5 is the node, then 2, the left child, is less than 5, but this 8, which is r for node 5, is greater than 5. So if you want to see a greater value, go towards the right. If you want to see a lesser value, go towards the left. That is how the binary search tree works in general. And here you can also see, if we take this node 8 as n, then it doesn't have any left value, but it has this right value, which is again greater than n itself. So that's what a binary search tree is in general. Now let's talk about an AVL tree. An AVL tree is a binary search tree which can rebalance itself, and that means that there should be some trees that are going to be imbalanced. Now, how do we decide if a tree is balanced or not? That is using something called a balance factor. This balance factor is based on the height of the tree, and we check the height using a formula. So let's say if we have a tree which looks like this. So let's say we got a tree which has 30, and then we have, let's say, 20, and then we got 10, and then let's say this is 25, and then we got 40, and then, or this should be 40, 40, and then we got 50, right? So if we have these set of nodes, that means that we can calculate the height by looking at the left tree and the right tree and see how many children deep are available. The formula for the balance factor, or BF, is you essentially minus the right height or the left height from the right height. So you see how many items are towards the right. So let's say if we want to try to find the height of this node 50, right? This one. If we wanted to find this one, then we need to see how many items or how many children are towards the left and towards the right. Now the thing is that there are no items on the left or on the right, which means that there is no height available for this node. So this height would be 0 for this particular node. Now, if we have a look at another item, let's say have a look at 40. Now 40 itself has no children on the left side, but it has one child towards the right side here. So the height somehow becomes right height minus left height, which means that here in this particular case, we got 1 minus 0 for the node 40, right? Now the balance factor, when we are calculating it, is going to be equal to 1. So if we have a positive value, then we call this particular tree or this particular node a right heavy node, which means that it is heavier towards the right side. Right? Now let's talk about this particular node. Here you see that this 30, if we start looking into this 30, that has two children towards the left. One is this 20, right? So this is the 20, and then we have 10. If we have calculated both as 1, if we count both as 1, then the height towards the left becomes 2. So this node 30 that we are talking about has a left height of 2 and has a right height of 2 itself because it has two nodes towards the right, 40 and 50. So if we follow this particular formula, so in this case we would have this situation where the right height is 2 and the left height is 2 as well. Now, according to the balance factor, if a particular tree has a value of either -1, 0 or 1, this is going to be called a balanced tree, right? It could be a left heavy balanced tree or right heavy balanced tree, but it is going to be a balanced tree as long as this formula, the balance factor, returns a value with -1, 0 or 1. So you need to understand that. Now, we already saw about some of the nodes. We could also talk about more nodes, but I don't really think that's going to be helpful. So now let's talk about a tree that is not balanced at all. So what I'm going to do is I'm going to remove a couple of nodes from here. And now let's see what is the height of particular node. So we are going to start from here, from 25. So if we look at 25, it doesn't have anything here. It doesn't have anything here. So no left tree, no right tree. The height of this node is 0. Now, let's talk about another node, and that is 10. This 10 doesn't have anything, and the height of this node is 0 again. Now, let's talk about another node that is 20. 20 has one child here, right? And one child here. So you see that the left becomes 1 and the right becomes 1. If we put it to the formula, the balance factor of this one becomes 1 minus 1 equals 0, and this is balanced. No problem at all. Now, let's talk about this guy, which is 30. How do we see this working? Is this balanced or not? First of all, it does not have a right tree at all. Secondly, if we go towards the left side, this is 1. So this is one child, and then this is another child. So 1 is 20, and then the second child is 10. So it goes all the way to 10 and has a height of 2. If we put this into balance factor and then we say right child or right height, which is 0, minus the left height is 2. This gives us the factor of -2. Now this means that we have an unbalanced tree. This is not a balanced tree because it is not -1, not 0, not 1, but it is -2. And this is a problem for us. Now, an AVL tree is a tree which will refactor or rebuild itself. So we need to see how do we balance something. We balance trees using rotations, but even before so, we need to understand what is a rotation and what we see before applying a particular rotation. Now notice in this case, in the example that I've shown you, that we have got the value of -2. This -2 essentially tells us that this tree is a left heavy tree because you can see that this is going towards the left. We have left child or left children or left nodes, but this 30 doesn't have any right child. So it's not right heavy because it's left heavy. We have more items on the left, we don't have items on the right. So this is called left heavy tree. So I'm going to actually remove that just to avoid confusion. So when we have a left heavy tree, we apply something called a rotation, and the rotation means that we try to adjust those nodes. So we are going to look at an example. Let's say we got 30 here, and then we got 20, and then we got 10. So I'm keeping it simple for now. This essentially means that we've got a left heavy tree. How do I know? Because we can see that if we go towards the left, we get 1 and 1, which means that this 30 node has 2 children. So this is 2 on the left, but we have nothing on the right. So we have 0 on the right. And if we see the balance factor, it's 0 minus 2, which means -2, which means left heavy. So we got a left heavy tree, right? So this left heavy tree is going to essentially, and this is a left heavy imbalanced tree because it's not -1, 0 or 1. Now, how do we fix this? When we have a left heavy tree that is an imbalanced tree, we need to balance it using something called a rotation, and there are 2 rotations that we can apply here. One rotation is called a right rotation, and another rotation is called a left-right rotation. So this is what we usually do. We are going to look at these things one by one, so don't worry about it. Let's consider another example now. And it's going to be an opposite of what we just discussed. We're going to have a tree, but it's going to be a different tree. So let's say we got 30, then we got 40, and then we got 50. Now this tree, you can see that we don't have any elements towards the left side, but we do have elements towards the right side. So if I have to find the height of it, the right height would be 2 because it's 0, 1, 2, but we don't have anything on the left. So the left height is actually 0. If we put that in the formula itself, you can see that in this particular case, what we would get out of it is we're gonna get the right height, which is 2, and then minus left height, which is 0. So we get 2, which is a positive 2, and that means that this is a right heavy tree. When we have a right heavy tree, we can apply two sort of rotations. We can apply a left rotation, or we can apply a right left rotation. Now don't be confused about these number twos, because it seems like they are a bit weird, but when I'll teach you, you'll understand how those works. But we are going to first look at right rotation and left right rotation. So let's first have a look at the left heavy trees and the right rotation. So here we're going to see the example of 30, 20, and then 10. In this particular case where we have a tree which is left heavy, so we have a left heavy tree and we are applying a right rotation. The right rotation means that this 30 is going to come towards the right side. This 20 is going to go up. So essentially we take care of these two elements. We kind of move them in a way that they go towards the right side. So that means that this 30 is going to come here. This 20 is going to go and take the place of 30 like this as a root node, and then the 10 still remains the same. Previously, this 20 had a child that was 10, and now still it has a left child that is 10. So that is exactly the same. What has changed is that previously this 30 had a left child called 20, but now this 20 has a right child called 30. And this is still a binary tree, because you can see that if we want a smaller value, we go towards the left. If we want a larger value, we go toward the right. So it's still a BST or a binary search tree. That also follows. So this is how you would rotate a left heavy tree with a right rotation, right? So I'm going to just put here and say this is a right rotation. The next thing that we are going to discuss is right heavy tree with a left rotation. So it's completely opposite of what we just discussed. So what we are going to do is that, let's suppose we have a right heavy tree, and I'm going to draw it really quick. So let's say we have a 30, and then we have 40, and then we got a 50. In this particular case, this is a right heavy tree because you can see that we got children towards the right, but we don't have any children towards the left. So this node 30 has no children or no left child, but it has one right child and then second depth of the child. So this becomes, the right height becomes 2 here. And then if we kind of take formula in, so the balance factor is right height minus left height, which means that we are doing 2 minus 0, and then that means 2. So we got an imbalanced tree because it's not 1, not minus 1, not 0. So we got a problem here. Now, how do we resolve this? We use the rotation that we call the left rotation, right? What we do here is that we essentially rotate this to the left side. Now, what would happen is that these two nodes are going to be moved. So these two nodes that you see, the 30 and 40, these are going to be moved just towards the left side. And what happens is that this 30 comes like this, and then this 40, this takes the place of 30. 30 comes here, and then 50 comes to this place. So essentially, it's kind of the left rotation as we discussed. So it becomes something like this, 40, 30, and then we got 50 here. So now you see that we have a situation where this is still a binary search tree. You can see that for a smaller value, we go towards the left. For higher value, we go towards the right. And each left child is lesser than the node and each right child is greater than the node itself. And if we try to see the height now, the height is balanced. How? Because if this node, if we talk about the node 40 here on top, it has a left child 1, right child 1. We subtract and get out the balance factor, that becomes 0, completely balanced. If we see the height of this 30 here, we see that it has no left child, no right child, so it has a balance of 0. Similarly, the 50 has no right or left child, so it has a balance of 0. So from the balance factor of 2, we came now to a balance factor of 0. That is a success with the left rotation. Now we are going to talk about another sort of example in which we have a left heavy tree, but we need a left right rotation. So considering the same example or similar example per se, we got 30 here, we got 20 here, but let's say the next value that we get is 25. I'm going to quickly remove and write it again, 25 here. Now in this case, we have a different situation. We cannot do the left rotation as we discussed before. And the reason for that is if I do that, then that would become 20, 25, and then 30, right? because if we follow the same pattern, that's what would happen if we apply the left rotation. Now the problem here is that now this is not a binary size tree. Why? Because this 25 that you see here is greater than 20, and we already discussed that in the binary size tree you go to the left for smaller values, you go towards the right for higher values. So this node cannot have a left child which is higher than itself. So this situation would not be fixed with a left rotation, unfortunately. So we need to implement something called the left right rotation, or LRR. So how do we do that? First, we apply a particular rotation to these two nodes. We basically rotate them left, and then we apply the right rotation to these two nodes, or whatever those would be. So first of all, these two nodes, these are going to be interchangeable, which means that this situation would become something like this. So this 30 would still be here, but then here we would have a change. We would have a 25 here, but since we rotate it, this becomes something like this. So previously we had 20 having a right child called 25, but now we have 25 having a left child of 20. And the connection is different as well. This 30 had 20 as the left child, but this 30 now has 25 as the left child. So we have changed something here. Now, do you see that this looks quite a lot like our previous situation where we had a left heavy tree? It looks exactly like this one because we have applied the left rotation. And now since it looks like the left situation or left heavy situation that we already discovered, now we can apply the right rotation to this case. So first of all, we have applied the left rotation, and now we imply, or actually let's make it left rotation here, and then we apply the right rotation, and that would mean that we apply this to these two elements, 30 and 25. So when we apply this, then 25 takes the place of 30, 30 goes toward the right side, and 20, since it's with 25, it comes along. So what happens is that we say 30 goes towards the right side, this 25 comes towards the top, and with 25, this 20 comes along because it was already a left child of it. And in this particular situation, you see that we resolved this particular heavy tree, but with left-right rotation. Now, why did we need another one of those? Because when we applied the left rotation to this node, did was we replaced these, but still, if you look at that, the balance factor still is 2 because we have two elements towards the left side, but nothing on the right side. But now that we have applied left rotation plus right rotation, you can see that now we have a balance factor of 0 because this has 25 node has this child and this child. So means 1 minus 1 equals to 0 as a balance factor. So we went from balance factor 2 to balance factor 0. Now we are going to talk about another situation where we would have a right heavy tree, but we have to apply something different. So let's say we have an example where we have 30 as the top node, then we got 40, then we got another node called 35. Now again, this is not a really simple one, so we cannot apply just a left rotation. This particular node is right heavy. Why do we know that this is right heavy? Because this 30 doesn't have any left child, but it has 1 and 2 elements towards the right tree, which means that this is right heavy. Now, if we apply the left rotation to this will not work. So we need to apply something called the right left rotation, or we call it RLR. Now, that means that first we need to apply the right rotation to this one. The right rotation would mean that we are going to touch base these two nodes, the 40 and 35, and we are going to rotate them towards the right side. We are going to flip them. So when we do this, the 30 at the top still remains the same, but this 35 here, this takes place of 40. And then 40 goes away because it's going to go and become the right child of 35. So here 35 comes in like this. And now since 40 is greater than 35, it goes just like this here, right? And now you can see that we still have a binary size tree because every right child is greater than the node. This 35 is greater than 30. This 40 is greater than 35. So it's not a balanced tree, but it's a binary size tree. And we still have the same balance factor, which is 2, because you can see that there's still no left child, but there are now 1 and 2 right children, right? So we got a right heavy tree with a balance factor of 2. Now we are going to apply the left rotation to this. So again, we first apply the right rotation to these folks, but then we apply the left rotation to these two, 30 and 35. So we are now going to consider these two nodes. So I'm going to take those and then flip 30 and 35. So what would happen is that 35 would come on top, taking the place of 30. Then since 30 is a small child, it will go right here, so down towards the left, so it would become 30 here, and then 35 already had a right child called 40, so it's going to keep and maintain that. Now you can see that this tree is balanced because this 35 has a left tree height of 1 and a right tree height of 1 as well, so 1 minus 1 equals to 0. We got a balanced tree here. So now let's talk about what distinguishes when we want to use a left rotation or a right left rotation. So let's talk about, we have a tree that is a left heavy, which means that we have 30, 20, and 10. This is a left heavy tree because tree height on the left side is 2 and the tree height on the right side is 0 because it doesn't have any right tree, but it has 1, 2 nodes on the left side, right? Now, if we have a situation where the node that is imbalanced, which is in this particular case 30, we check the immediate left node of this one, this 20. And we check, is it heavier? Is this node heavier on the left or on the right? If the node itself is left heavy and the node's left child is also left heavy, then we use the right rotation. And it is left heavy because it doesn't have a right child as well, right? So we're going to use right rotation. Let's suppose we have another situation here. We have 30, then we got 20 here, but this 20 has a child which is 25. In this case, we have a different situation. In this case, the node in question, which is imbalanced, is 30 because it doesn't have anything towards the right, but on the left subtree, it has 1, 2 nodes. So it becomes 2 on the left side. So it's a left heavy tree. But then if you look at it, this node is left heavy, but its left child, which is this 20 is not left heavy. It's now right heavy because it has 1 on the right side and it has 0 on the left side. So this node 20 is essentially right heavy and this 30 is left heavy. Do you understand it now? Hopefully you do. So in this particular case, instead of running the right rotation, we do something called left-right rotation that we just discussed. So now let's go towards another example of the opposite case. So in the case of having a right heavy tree, we would have something like 30, 40. We have exactly the same situation. We don't have any left child, but we do have the right side having 1 and 2 depth of the child. So this is a right heavy, right? And then you also see similarly in this case about the other situation where we have this node having 30 and then let's say we got 40, but then this 40 had a child which is 35, right? So in this particular case, we still have a right heavy tree because no child on the left, but there's 1, 2 child on the right subtree. So this becomes again 2 as in all. Now, in this particular case, we need to show the same thing. We need to identify the node in question. This is right heavy. So we say this is RH, which is right heavy. Is the right child of this node, is that also right heavy? If this is also right heavy, which it is, you can see there's no node on the left side, but there's one node on the right side. If this is on the right side as well, then we use the simple left rotation. So we essentially rotate this to the left side. Simple left rotation, nothing fancy. Or the other case where we have this 30 in question, we see that this is right heavy. We already know that because of this 2. But is the right child of this also right heavy? And it's not, because you can see that there's no right child, but there's a left child here. So this particular node is left heavy. You can see that there both of these had right heavies, but here we have a left heavy and the right heavy. So that's why instead of running just a simple left rotation to avoid this right heavy, we run something called a right left rotation that we just discussed. Now I hope that you understood this. If you did not, let me know in the comments. We might do some session or live stream where I can explain this even better. But having said this, we are now going to go and quickly test it out and start implementing in the code. So to start implementing this in JavaScript and follow along with me, what you need to do is that you need to go to github.com/ahsanayaz/fun with JavaScript. The link should be already in the description. And then you need to click here and copy the code here. And then you need to open your terminal or your command prompt and type git clone and then just this URL. Once you do so, you should see a folder created. And then you need to open this into VS Code or whatever favorite editor you have. And then you need to see that you have the folder fun with JavaScript and the branch set to main. You need to do git checkout AVL Tree start or AVL-tree-start. And once you have checked it out, you need to run npm install. This will install any dependencies of this package. And once you are done doing that, you need to run npm start. This will start the server and you should be able to see the application itself. I've already done that and it started the server, so we are not going to look into that. But if I go here on my browser, localhost 8080, I should be able to see my app running. And then I can quickly go and select JS AVL tree. And this is the project that we are working on. Right now, this is just a binary size tree, so it's not balancing itself. For example, let's make this a right heavy tree. If I add the value 60 here, this now becomes a right heavy tree. You see, it says balance tree, but this is just the final output. So don't worry about this one. We have not implemented it yet. So you see that 30, 50, 60 is a right heavy tree. We have 2 factor on the right side and on left we have 0. Now that we have this, let's talk about how we implement this. So first of all, you need to go to main.js, inside source projects, JS AVL tree, and then just pick the left heavy tree for the example. So you can paste it on line number 10 from line number 16. And when you do so, we should start seeing the example of the left heavy tree, which is 30 and 20 here. Now, if we go to our JS AVL tree, you will notice that here it just exports the binary search tree, which means that our whole system is just a binary search tree. It's not an AVL tree. So how do we implement that? First of all, we create a class. So we say class AVL tree extends, and then we say binary search tree, and then we export default this AVL tree. Now, first of all, we need to find a way to calculate the balance factor. And we already know that the balance factor has a formula, and that formula is right here. We essentially subtract the left tree height from the right tree height. So right tree height minus left tree height. And we already know how to calculate that. So for that, we are going to create some constants. So here we are going to say const balance factors. And here we are going to say the left heavy is -1, the balance is 0, and the right heavy is 1, right? So whenever there is a left heavy tree, we are going to do a right minus left, which means that we are going to get a negative value when there's a left heavy tree and a positive value when there's a right heavy tree. Now we need to implement the function for getting the node height. So a node's height is essentially the maximum of either left tree or the right tree. So either of those, we get the maximum out of that, and then we calculate and we say that the maximum height. For example, for this node 20, maximum height is 1 because 10 and 25 are only children and they are like at 1 step from them. Similarly, this 30 has 0 as the right height, but on the left, it has essentially 2 items. So 20 and 10, or 20 or 25, either way, we have a height of 2 for 30. So we're going to go and we are going to code this in a way that we say something like get node height, and then we get node, and then essentially we need to just do this. So if we have a node that is null, we count that as a -1, and then here we say something like math.max this dot, and then we essentially use get node height of the node.left and the node.right, and then we just add a +1 in the end of this math.max, and that is essentially our node.height. So now that we have this, I'm going to go to the main.js, and here we are just going to do a couple of things to see all of this working. So first of all, I'm going to say window.avl tree equals AVL tree, just to make sure that we get this and we can log this and use some functions around it. Then what we are going to do is that we are going to essentially create a function called get balance factor, and this get balance factor is going to check and return the balance factor out of it. So first of all, if the node is null, as GitHub Copilot says, we're going to return 0. That means that we are talking about these X marks, so there are no nodes here, so the height is 0. But if there is a node, then we need to do node.right minus node.left. So now that we have got the balance factor and the AVL tree itself, we are going to do some quick tests, and then we are going to implement further stuff as well. For example, I'm going to go to main.js, and inside here for the left heavy tree, we can add, let's say, the value 10 here as well. And if I go to my AVL tree here, we should be able to also log this. So I'm going to, or actually we can do window.avl tree, and here you see that we got this root node 30 and the whole tree here. So I can do AVL tree dot get node height, and if I do that, let's see what happens. I'm going to say AVL tree dot root, and I don't really need to say window here because it's global. So you see that the height here is 2, And that is because we have at max 2 elements from this 30. Now don't confuse the height with balance factor. The balance factor is a bit different. Get balance factor gives us -2. Because this is a left heavy tree, we essentially do the right minus left, which means 0 on the right minus 2, which gives us this -2. If we had a right heavy tree, then that would have been different. So let's say if we add a couple of steps to make it right heavy, something like this. So that would make 40, 50, 60. And if I do the same thing here and refresh, then we can see what comes out of it. So in this particular case, if we check AVL tree dot get node height, and then we do AVL tree dot root, and if we do this, you see that the height is 3. Why? Because on the right side it has 1, 2, 3, and on the left side it has 1, 2. So that's why we got 3. Now for the balance factor, let's see what happens. So get balance factor, and now you see here the balance factor is 1. Now you would be like, hey, why is this 1? Because we do right minus left. The right is 3, the left is 2, so 2 minus 1 equals to 1. So that's fine. If we added another 1 to this one, then we got a problem, because so far 0, 1 and -1 means we have sort of a heavy side of tree, or a left heavy or right heavy tree, but still it's balanced. When we have a -2 or 2 or greater, then we got a problem. So now if I try to do the same thing, and if I do AVL tree dot get balance factor, and then if I do this, we get a 2. Why do we get a 2? Because we have here 1, 2, 3, 4 nested elements, but here we have just 2. So 4 minus 2 equals to 2. Now we got a problem. So I'm gonna actually go and revert this now that we have checked this. So I'm gonna quickly go and remove all of this. I'm gonna comment this one, so we get the initial state of this. Now let's start implementing the rotations. So first of all, I'm gonna go to AVL tree here, and now we are going to talk about some things. So first of all, even before rotation, we are going to implement that into insert. So insert value, and then here we do something like this, what GitHub Copilot would suggest. So we got node equals to super.insert value, and then we also return the node itself. Now what's happening here is that we are calling the insert method of super class, which means that we are saying, hey, for this AVL tree, whatever binary search tree does, just do that, which means that add this to the tree as a binary search tree would do, but then also rebalance it. So this is an additional thing that we are doing right here. Apart from that, everything the binary search does, like here, this is all the code of the binary search tree, which you can see in the video as I mentioned. You can implement that, but apart from that, we are just rebalancing it. So we are going to implement the rebalance method here, rebalance node, and we are going to essentially apply some rotations here. But I'm not going to do all of this right here. Before that, we need to implement the rotations. So we're going to start with the right rotation first, and we are going to call it rotate right. So first of all, we say rotate right, and we say node here, and then we start implementing the situation here. So here you see that it says rotate right equals to node, and then it creates temporary variable, and then it switches it. So let's have a quick look at the rotate right situation. Now this one is the right rotation situation, where we have a left heavy tree, and we have this situation where we have 3, 30, 20, and 10, and we need to rotate towards the right side, which means that this 30 had a left child 20, but now this 20 will have a right child of 30. That's what's happening here. So according to Gitpilot, this is fine, but for me it's not. And that is because we also need to render this into the UI, so it's a bit more complex than that. So I also need to handle some logic around the parent, but this is essentially the idea of rotation. We essentially take a temporary variable, we assign the left child's right to the node.left, and then the left and the node itself to the left.right. That is essentially the whole rotation out there. So you can skip the rest of the things, but here I need to do some things for the parent itself. So I need to check the parent. So I'm going to say temp, or actually left.parent equals, and then we do node.parent. Similarly, we do something like node.parent equals to left. Then we check if the parent exists, the left.parent, because there could be a case where this node.parent is null, and that is fine. But if that's not null, and if it is assigned to left.parent, then we need to do something like this. So we can check if left.parent.left equals to node, then we apply left.parent.left equals to left. Otherwise, we do this. That kind of summarizes what we want to do. Now we're going to also implement another function called rotate left. It's going to be exactly the same. So GitHub Copilot will most likely help me out with this one. So it's exactly doing the same thing. Right parent, blah, blah, blah. I'm trusting this for now. And now we can talk about the other functions as well. So we also have another function called rotate left right, and then rotate right left. So here I'm going to use this. So what happens in rotate left right is that we first use the rotate left on the node.left, and then we go towards rotate right. Let me quickly explain to you according to our example. In this particular example, you can see that we have a rotate left right situation, situation in which we first have this node 30. This 30 has a left node. So in order to do left right, we first apply a rotation left to the node dot left. And that's what we are doing here. We are saying that rotate left the node dot left, which means that, hey, take the 30, which is node, but then apply rotate left to 20, which is the node dot left. And then we apply the right rotation to this node 30, so it comes towards the right side just like this, and then the rest of the things comes along the way. So here we do exactly the same thing. Rotate left on the node dot left and then rotate right on the node. Similarly, we are going to do the same thing for rotate right left. We're going to say node here, and then we are going to basically have the same code but just in the opposite way. Now that we have this, we need to implement the rebalance function, which is the main function right now. So what we are going to do is we are going to start with checking if the node is null, because if that's the case, we don't need to rebalance anything. So we are going to say something like if node equals null, or if not node, then we just say return, right? Otherwise, we first get the balance factor of this node that we are talking about. Now, there's one important thing to know. When we add a node into this tree like this 10, what happens is that this is the node that we get in the code. So we start balancing from this 10. Then we go to 20, then we go to 30. So we go from the bottom to the top, or the element inserted to the top, or the element removed to the top. In either case, we need to evaluate all of this tree and make sure that we are balancing each of those. So in this particular case, we are first going to go to either 25, and then we are going to go all the way top. So what we do here is that in the end, we are going to say if we have node.parent, then we do this dot rebalance node.parent. But let's say the node.parent doesn't exist. That just means that this element is the root element. So we can say else this dot root equals to node. Now let's talk about balance factor. So let's say the element in consideration, let's say 30 comes in, and then we check, hey, is this left heavy or right heavy? So we get the balance factor out. Then we put the condition of if the balance factor is left heavy, but not just left heavy, which means that this is not -1 or 1 or 0. This is either -2 or 2. So instead of just considering this equal to left heavy, we are going to go beyond that and say less than balanced left heavy. If that's the case, then we need to implement some code. We need to here say that, hey, so here we check, hey, if this is less than balance heavy, then we get the factor of node.left. We check if this node.left is less than balanced, which means that it's -1. Is the node's left child also left heavy? When that's the case, then we apply the right rotation. So here we are going to check exactly the same thing. So we are going to check in the code here that, hey, if we have a left heavy case with something like a -2, right? Then we check if the balance factor of node left is also less than balanced. I mean, also we could just say equals to left heavy for readability. So we can say balance factor dot left heavy, not right heavy. Left heavy, we need to say node equals this dot rotate right, and then we just pass the node. If it's not the case, then we do else, and here we say node equals this dot rotate left right, and then we say node. Okay, so that's what we do, and I'm just gonna remove the return from here. We don't need that. So this is the case for what we are talking about, the left heavy case, right? So if I go and check this out now, let's see what happens. So I'm gonna go here and then insert a node, insert the value 10 here, click OK, and you see, woohoo, we got the balanced version of this tree, and now it has balanced itself to be what we just discussed, 10, 20, 30. So you see that it's working. It's applying the right rotation. Now let's see the other case where we have to apply the left rotation, right? Or the left right rotation. So in that case, I'm going to go to main.js, and then instead of left heavy tree, I'm going to take the left right heavy tree. So I'm going to go here and apply this, and now we are going to refresh and see the same thing. So now if I go here and say, let's say we add a 15, which means that it's going to have 30, 10, but then not a left child, but a right child. So it's going to go into the second situation that we talked about, which is exactly this one. So left, or node left, but then right. So node left, but then right. So if I click OK here, boom, we have a balanced tree. It would have been like this, which is 30, 10, and 15, which is imbalanced. It's a left heavy tree, but a left right heavy tree, you could call it, or probably is just a term that I use. But now when balancing it, you can see that it's 10, 15, and 30 in this way. And this is a binary search tree now, because you can see that the node has a lesser value on the left and has a greater value on the right side. So this is a balanced binary search tree, and balance factor of this one is 0. because it has 1 here, and right minus left, 1 minus 1 equals to 0, right? So we got this implemented. So we can quickly go ahead and implement the rest of the rotations. So now we are going to check else if we check the other case, balance factor is greater than right heavy, which means that this is a case of having +2, then I'm gonna let GitHub Copilot do this because it's kind of copying my logic, whatever I've written already. So here it's gonna do rotate left, and then else, and then rotate right left, and then going forward, and then this. This is still very convenient. So thank you, GitHub. So now if I save this, it should go ahead and do the exact same thing for me. So I'm gonna quickly go ahead and choose another example from main. So from the main, we are going to check first the right heavy tree. So we are going to replace the example here, refresh, and now we have a right heavy tree like 30 and 40. If I add another one called 50 here, that would make it a right heavy, but also a balanced tree. Yay! So you see 30, 40, 50, and it's balanced now because now we have 30, 40, and 50. This is a balanced tree. This one is not a balanced tree because it has 2 on the right side and 0 on the left side, which makes it 2. And now if I go ahead and try out the right left heavy tree, which is exactly the same, so I can probably use the same thing but just add something that goes here towards the left. So if I go here, and I think we discussed it in the right heavy tree as well, so we discussed this in the example as well, that this is sort of a right left heavy. So we have 30, 40, but then 35 here. So if I go ahead and do the same example here, add 35 here, you see that here it's balanced. Awesome. So we got 30, 40, and 40, 35 imbalance, but now here it's 30, 35, and 40. Awesome. So we got our tree completely balanced, and now we can have actually crazy amount of imbalanced trees and they would still be working. For example, we are going to go and see one example from a function that we have in binary size tree, and that is probably inside main, and we have this create sample tree data. So I'm going to actually use that. I'm going to copy this and go into main, and instead of using this right heavy tree, we are going to import, or actually it's imported here. I'm going to use create sample tree data. And if I use this now, we see a crazy big tree, which should be having insert method here. So we already imported here. So what I'm going to do is that instead of returning this, what I can do is from the function, I can probably just use const sample data and then do the same thing here. So I'm quickly going to create a function here. I'm going to create sample data, something like this, and then use the sample data. So if I refresh now, you see that we have a crazy tree right here, and we can remove stuff from there as well, but we have not implemented the removal rebalancing. So I'm going to go to JS AVL Tree, and here we are going to also add remove value, and here we are going to do the exact same thing. We get super.remove, rebalance, and node. So I'm going to refresh now, and now I'm going to remove this node 15 to make this completely imbalanced. So if I remove the node 15, let's see what happens. So if I remove this, you see that we got this 15 removed from the balance tree, and this 18 from here came back all the way top here to 15. So you can see that the 18 came here, and then the 20 and the 25, they are still there. So we made this sort of imbalance. Now I can keep removing this 18 or some other nodes as well. For example, I can now remove 18. It's going to bring 14 up top. It brought it from here. So from here, 14 jumped over to top 18, and now you can see that it's applying different sort of rotations right here. So now our functionality for the whole tree is completed, and this is the AVL tree. So I hope that you liked the video. If you did, press the thumbs up button. If you learned something new, share in the comment. I love hearing feedback from people who learned something from my videos, so that's going to be awesome. If you have not subscribed to the channel, please do that. I stream on Twitch and YouTube, do live coding, so please make sure to join in. And if you have not joined this Discord, you are missing a lot of communication between different developers. So join the Discord and let's build this community together. At the end, if you have watched this whole video, just comment in the comment box that, hey, I've watched this video till the end, and let me know what was your favorite part about this video. Till the next time, take care of yourself and happy coding. I'm going to see you in the next one. Bye.